Hi, I'm Professor Yue Jessica Wang from the University of California, Merced, and today I'd like to tell you about adaptability. As species, we evolve through the survival of the fittest by constantly adapting to new environments and new situations. Wouldn't it be great if materials can learn to do the same? Take electronics, for example. Laptops, phones, and smartwatches are now pervasive in our daily lives, but they are prone to damage under impact, and that is why we protect them with cases and padded backpacks. But for the next generation of electronics, we envision them to be more intimately integrated with the human body so that they can provide better biometric monitoring for our health. This will require the electronic materials to be soft and to deform with our body movement. This also creates a new challenge. If the electronics are directly attached to our clothes or our skin, we can't protect them with cases anymore. Our body moves at different speed depending on our activity, and materials and devices break more easily when we move rapidly, like during sports, or when we get hit by a soccer ball. So you see, there can be a huge advantage if we can make wearable electronics adaptive to impact or the rate of deformation, so that they can protect themselves without protective case. So how do we make this happen? Believe it or not, we found inspiration from cornstarch slurry. We can easily run our fingers through a cornstarch slurry, but when we hit it suddenly with force, it becomes harder like a brick and resists penetration. This is exactly the kind of adaptive properties we are looking for. So we designed an electronic polymer with structures similar to coagulated cornstarch particles in a solid state. The result is an electrically conductive polymer that is highly stretchable and can heal itself like our skin. And when we test out its deformation behavior, you can see that when it's pulled at a relatively slow rate, it can deform by a reasonable amount before breaking. So what happens if we deform it faster? Well, intuitively, we know that faster deformation will cause most materials to break more easily. But this material does the opposite. It becomes much stretchier and tougher, analogous to what we have seen with cornstarch slurry. In other words, this electronic material is able to dynamically adapt to the rate of deformation or impact. They can protect themselves when accidents occur. As we worked on this project, we thought, why don't we take this concept further and think about how else can we create adaptability? We found a lot of inspirations from nature. For example, tree branches can adapt to the direction of the wind without breaking. This is largely because of cellular structure of trees, which provides both strength and freedom for the trees to bend and recover like an elastic band. So we set out to do the same with electronic polymers. Complex 3D structures require 3D printing, so we developed new methods to 3D print conductive polymers using light, which allow us to obtain well-defined architectures at high resolution. So how do these materials behave mechanically? Well, when we have a solid chunk of this conducting polymer, you can see that it's very brittle and shatters under minor compression. But when this exact same material is printed into cellular structure, it becomes elastic and can recover from significant deformation, just like tree branches. So that's a new form of adaptability that we have infused into electronic polymers. Once we started to look to nature for guidance, inspirations just kept on coming. While we mainly focus on soft electronic materials, we recognize that conventional hard electronics have irreplaceable advantages. For example, it's much easier to type on a hard surface than a soft one. We came across this organism called a sea cucumber. It's typically soft and jelly-like and can squeeze itself through thin channels, but in the presence of threat, it will harden to protect itself. In other words, it is able to adapt its mechanical properties to the environment. So we thought, wouldn't it be great if we can make electronic materials do the same? So we create a material that can transform between soft and hard states, just like sea cucumbers. You can imagine wrapping a device around your wrist in soft state, but can take it off and transition it into hard state when you use it. As we work to mimic the amazing adaptive properties of nature, a thought occurred to us. Instead of copying nature, is it possible to directly employ nature to do the design work for us? We got fascinated by an organism called Plycerium polycephalum, or commonly known as the slime mold. This mold does not have a brain, but it can solve puzzles and design city transportation systems as if it's a seasoned engineer. So we invited this organism into our lab. We're currently having this mold design load-bearing networks, and then we'll change the location or distribution of the load and see how the design from the slime mold will adapt to this change. After that, we'll take the design and 3D print them into real structures to analyze their mechanical properties. We're very excited about this new direction and are curious to see where slime mold will lead us. We're grateful for support from Arnold and Mabel Beckman Foundation. Dr. Beckman was visionary. He saw outside the box. He took risks with his research. He tackled fundamental scientific challenges, but also transformed them into instruments. We strive to honor his legacy by creating new materials through fundamental chemical and biological design principles, with a goal to eventually advance applications that can better human lives. We thank Dr. Beckman for inspiring us, and the Beckman Foundation for making our work possible.